In part 2 of our Kinematics Tuneup, we look at a velocity versus time graph. And the first piece of information we would like to know is the one thing we cannot determine, and that's your position at any particular time. There's a missing piece of information in a velocity graph, and that's your starting position. And if you don't know where you were at the beginning, then you can't know where you are at any future time. This is related to that constant term that you have to tack on when finding an antiderivative. Some extra piece of information is needed to tell you what that constant term is. And so likewise, here in a velocity graph, some extra piece of information, such as your starting position, is needed if you want to know your exact position at any time. Now, you may be thinking, wait, doesn't the area under the curve on a velocity graph tell you about position? And yes, indeed it does. My next tune-up tip is a reminder that an area is always a delta. An area on any graph represents a change. It tells you a final value minus an initial value, but it doesn't tell you the final value or the initial value. It tells you the difference between them. That's what you always get from an area. So next, let's turn to trying to find that displacement, the change in x. This it's possible to get from our velocity graph, the change in x. And our definition as x relates to velocity might come from this integral here. So we think, okay, we just have to integrate the velocity graph from time 1 to time 2 if we want the displacement from time 1 to time 2. But you cannot find the integral of a graph. It doesn't make sense to say that. You find an integral of an equation. We don't have an equation. We just have this graph. So what we can do, what we should say, is that we are going to estimate the area under the curve on the graph. And that estimate of the area is going to determine our displacement. So that's the language we should use. We should say that we're going to find the area under the curve to estimate our displacement here. Okay, so regarding the area under the curve, I want to examine that language here. We say under the curve, but that's not exactly what we mean. Consider a graph like this. Now, normally, 0 is located here by convention, but sometimes the 0 might be put somewhere else. Say that what if the 0 is up here? So these are negative values, and these are positive values. If 0 is here, and we want to find the area, then what we really mean is the area between the curve and the 0 axis. So if our 0 axis is here, and we want to find the area from this moment in time to this moment in time, then the area we want is that between the curve and the 0 axis. So not the gray shaded area that I pre-shaded, but this area here. Okay, so it's a bit cumbersome to say between the curve and the 0 axis, so we say under the curve just to make it shorter and simpler, but this is what we actually mean. And we should note then that an area there would be considered negative. Your area under the curve negative versus these areas above, sorry, your area underneath the 0 axis negative. These areas here and here above the 0 axis positive. All right, so let's find that area from 2 seconds to 9 seconds. So from here to there, this area. Okay, we should be sure to check the axis labels for the scale. Check the scale on the axes. The axes might have different scales. So we see that each box is worth half a meter per second. There's our unit, meter per second. Each box this way is worth 1 second. So one particular little box has these dimensions, 1 second and half a meter per second. So the area of one particular box is 0.5 meters. I'm going to come back to the question of these unit cancellations here in a little bit. So we see that one square has an area equivalent to a displacement of 0.5 meters. Remember that our areas are changes. Every area is a change, a delta. So a little box is a little delta of 0.5 meters. And so if we want the area under the curve from here to here, then we just count up all the boxes. So I see about 11 squares roughly inside that area times half a meter per square. So that gives us the 5.5 meters, and it's negative 5.5 meters since we are below the 0 axis here. So this indicates that our object moved in the negative direction this far between this time and this time. Okay, hence negative, our velocity was less than 0, that area was below the 0 axis. Okay, let's see, before we move on, I want to discuss what do you do if you're looking at one of these graphs and you know that the area has a certain meaning, and you know maybe that the slope has a certain meaning, but you forget which is which or what the significance of the slope or area might be. So here's a general tip for how to work out the meaning of this slope or area on a given graph. And I suggest you look at the units on the axes. A slope is always a rise over run. So a slope has units. Its units will be the units on the y-axis divided by the units on the x-axis for rise over run. Likewise, an area is always sort of a length times a width if you imagine a rectangular area. And an area has units as well. It'll be the units on the y-axis times the units on the x-axis for the length times the width. For example, on a velocity versus time graph, our slope, rise over run, that'll be our y-axis units, meters per second, divided by the x-axis units, seconds. So, okay, meters per second divided by seconds. If I divide by seconds, it's equivalent to multiplying by 1 over seconds. So meters per second times 1 over seconds gives us meters per second squared, which we recognize is the unit for acceleration. So by examining the units, I can remind myself that, oh, the slope on a velocity graph, that represents acceleration, because that's what the units work out to be. Now, how about the area on a velocity graph? Length times width. Okay, so meters per second times seconds. And here we see seconds cancels out, leaving us with meters. Okay, so the area represents some distance or position. But it can't just be position, because an area is always a change, a delta. So this must be equal to the change in position. So there you go. Examine the units to figure out the significance of the slope or area on a graph if you forget the significance of the slope or area on some particular graph. All right. So moving on from there, let's see, our distance traveled over our whole interval from 0 to 16 seconds. Recall that we just add up the magnitudes of the displacements. So we went backwards 5.5 meters here, and then we went forwards this distance. Compute that area. It's 12.5 squares, so it's about 6.3 meters. So add those two distances together. And recall that we're going to round that off to an appropriate number of significant digits because measurements are never exact. Okay, instantaneous velocity. Well, it's a velocity graph, so we can simply read it off of the vertical. We can simply read that off of the vertical axis here. Don't overcomplicate things. If you've got a velocity graph, you read velocity right off the axis. So 1 meter per second. And then speed, just the magnitude of that. Okay, that brings us down here to average velocity, which I want to talk about in some more detail now. An average value in general, delta x over delta t. An average value, no matter what kind of quantity we're talking about, an average value can be found from the integral of that quantity over the interval. So what I mean here is if the average velocity over some time interval is the displacement during that time divided by the delta t, well, our displacement can be found from this integral here, v dt, integrated over that time interval. So this is our integral in the numerator over the interval in the denominator. So in our little velocity versus time graph, the area under the curve here that area we know represents the result of this integral, which represents our change in x. An area is a delta, is a change, is this integral. And the average value of the velocity would be this area divided by that delta t. So the average value would fall somewhere around there between the low value of the velocity and the high value of the velocity during that interval. Okay, likewise for acceleration, delta v over delta t, this would be this integral of acceleration over time divided by that time interval. So this integral is equivalent to a change in velocity, and this area here between the curve and the zero axis on our acceleration graph, take that area, divide it by the delta t, and what you'll get is the average value of the acceleration during that time interval. And that average value, once again, should be somewhere between the highest value of the acceleration during that time and the lowest value of the acceleration during that time. We see in this example that the acceleration spent more time up at a high value and then quickly dropped to a low value. So we'd expect our average acceleration to be closer to the high end here than to the low end down there. Okay. So if we want our delta x over delta t, then we've already got those areas from 0 to 16 seconds. The negative 5.5 meters we went backwards, the 6.3 meters we went forwards, gives a total displacement of that value divided by the 16 seconds. Okay, so there's our average velocity. Note that even though we had the velocity graph, we couldn't read average velocity directly off of the axis here. Average velocity has to come from this definition, so we need the areas first. If you've got your velocity graph, you got to find the area first, divide by that time, and that gives you the average value of the velocity during that interval. Okay. Average speed then, total distance over total time. We've worked out the total distance that you traveled over those 16 seconds. And then moving on to change in velocity. Change is final value minus initial value. We can just read off the final and initial values off of the axis here. So 8 seconds to 10 seconds. 10 seconds looks like we are at half a meter per second. At 8 seconds, we were at negative 0.5 meters per second. So final value 0.5 minus initial value negative 0.5. Our velocity increased, got more positive by 1 meter per second during that time. Okay, now change in speed. I want to point out a common mistake that would be made here. Your change in speed is not the same thing as the absolute value of your change in velocity. Now, speed is the magnitude of velocity, but change in speed is not the magnitude of the change in velocity. Note, change in speed is going to be final speed minus initial speed. So it's magnitude of v2 minus magnitude of v1. Clearly, that's not always the same as v2 minus v1 magnitude, as this case illustrates. Here, this was our final velocity and our initial velocity, so the delta v was 1 meter per second, but the final velocity had the same absolute value as the initial velocity. At the end, you're going 0.5 meters per second, but at the end, 0.5 meters per second forward, at the beginning, 0.5 meters per second in the negative direction. But the speed at the end and at the beginning were the same. So the difference in speed is actually 0. You ended up at the same speed at which you started, you just happen to be going in a different direction. So 0 is not the same thing as the absolute value of 1, reinforcing this idea. So don't make this common mistake. And while we're on the subject of common mistakes, going back to the average velocity question back here, this has to be the way that you find an average value using this integral over interval idea. Some common mistakes regarding average value. The change in v is not the same thing as average value. And also average value of, the change in v is not the same thing as average velocity. And average velocity is not always equal to initial velocity plus final velocity divided by 2. This formula looks like the mean of the initial and final velocities. This does not always give you the average velocity. It does give you the correct value only in one special case. If your velocity versus time is a linear function, so like this, if velocity of time is a linear function, then and only then does the average velocity lie exactly halfway in between the initial value and the final value. That's a special case. In general, this does not give you the correct value for the average velocity. So don't use this to find average velocity. Use this to find average velocity. Okay, last couple parts here. Instantaneous acceleration. Well, we've got a velocity graph this time, and so we can get our instantaneous acceleration from the slope of the tangent line. We want it at 11 seconds. So here at 11 seconds, I'm going to sketch in a tangent line. The graph was pretty linear during this time, so my tangent line kind of lies right on top of the graph, and then we want the slope of the tangent line. So we go up 1 meter per second, again, check the scale, and then over 2 seconds, so that'll be 1 meter per second divided by 2 seconds. Our slope will be half a meter per second squared. Remember your units and sig figs here. Lastly, average acceleration, delta v over delta t, from our rule earlier. There it is, integral over interval. This can actually be found from the slope of the secant line on this graph. If we're going from 0 seconds to 16 seconds, then we can draw in a line going from the initial position to the final position on the graph. So from 0 to 16 seconds, it's a very shallow slope on that line, but it makes the hypotenuse of a right triangle with this leg and that leg there. This leg represents your delta v. This leg is your delta t, so delta v over delta t is indeed our definition for average velocity. So our delta v, half a meter per second over this delta t, giving us that value for our acceleration. Round off to 2 significant digits here, include units.